Good morning, everybody in the room in Dubai, and hello, online audience, whatever time of day it is for you. Thanks very much for joining us for this side event, which is focused on Antarctic and Southern Ocean ecosystems, and in particular, the severe threat that they are under from climate change. So I'm Dr. Sian Henley from the University of Edinburgh, and I'm also representing the Southern Ocean Observing System. And those in the room can see some paperwork on your seats that you can take away and read about the Southern Ocean Observing System. And it's my great pleasure to be joined by great colleagues. So we've got Dr. Stephanie Arndt from the Alfred Wegener Institute, who will talk to us about sea ice changes in Antarctica. We've got Dr. Letizia Tedesco here from the Finnish Environment Agency, who will talk to us about the sea ice ecosystem and the importance of that. And then joining us online all the way from Hobart, Tasmania, Australia, is Dr. Elizabeth Shadwick, who will talk to us about ocean acidification in the Southern Ocean. So this session will walk through what the main climate change drivers and impacts are in the Southern Ocean, and importantly, what we need to do to safeguard them effectively from climate change. So without further ado, I will give a brief introduction to the importance of these ecosystems, and then we'll work through the other speakers talking about the various pressures on the Southern Ocean system, and then I will bring it all back together at the end to talk about how these climate change impacts are driving change and putting intense pressure on the ecosystem. So a lot of what I'm going to say is from the summary for policymakers from the Marine Ecosystem Assessment for the Southern Ocean. So this is a piece of work that's been going on for about the last 5 years, involves over 200 scientists from 19 countries. So a real international, collaborative, interdisciplinary effort. And if you want to have a look at the summary for policymakers, which was released just 2 months ago at the annual meeting of the conservation of the Commission for the Conservation of Antarctic Marine Living Resources, then the web link is there on the screen. So what the ecosystem assessment was based around is this image here, which shows firstly the sheer size of the Southern Ocean. We're talking about a really large area of the global ocean, and not only is it large, but it is hugely important for the wider global ocean because it's so well connected through ocean currents to the Pacific, the Atlantic, and the Indian Oceans. So it really holds a central place in the global ocean circulation system. And in order to do this assessment of the ecosystem, we divided this large region into smaller, more manageable regions, each of which have different biological and chemical and physical characteristics in the way the ecosystem works. So whilst these were divided up for the purposes of the assessment, it's important to note that, like in all ocean systems, these different regions are very strongly interconnected, and there is a significant links between all of them, such that changes happening in one or other of these regions have effects throughout the rest of the regions and indeed to further afield in the global ocean system. So this image here shows an overview of how Southern Ocean ecosystems function. We can see in the circles the different types of organisms that we might expect to see in the Southern Ocean, and the light blue arrows indicate who eats who. So we can see that this is an ecosystem which has very strong linkages between different organisms, whereby the primary producers, the phytoplankton blooms in green, and the sea ice algae in yellow underneath the sea ice there, are the organisms that conduct photosynthesis. And that means that they produce organic carbon, which is the basis of the entire food web. This carbon feeds the copepods and the krill, And those organisms feed all of the other larger organisms that we recognize as iconic Antarctic species. So this is a very highly productive ecosystem, and it has incredibly high biodiversity, which is both valuable for its own intrinsic value, but also has a significant role to play in providing ecosystem services to humankind, both close to the Southern Ocean and in countries much further afield. So the Southern Ocean has a very complex ecosystem structure. And what's particularly important is that these organisms are very well adapted to their environment. They've lived in a cold, fairly stable environment for many hundreds and thousands of years, because this ecosystem has actually been developing for the last 25 million years. So these are used to a stable, reliable environment where the sea ice comes and goes on a seasonal basis. And many of these organisms tie everything they do in their lives to the seasonal advance and retreat of the sea ice. But we're going to hear in the next talk that there are sea ice changes underway. And the important thing for the ecosystem point of view is that because these animals tie their life cycles so strongly to the sea ice, changes in the sea ice lead to large changes for these organisms to have to cope with. If we move to the next slide, this image here shows that connection between the Southern Ocean and elsewhere in the global ocean system. This is a very simplified version of the ocean currents that connect the Southern Ocean with the Atlantic, the Indian, and Pacific Oceans. And the reason that these currents are important is that they transport heat, nutrients, and carbon dioxide throughout the global ocean system. And in fact, the nutrients that come from the Southern Ocean play a large role in fueling ocean life as far away as the tropical regions, and therefore they play an important role in ocean health at the much larger scale. The Southern Ocean is also a place of extensive air-sea exchange of carbon dioxide, and this makes it a very important regulator of Earth's climate system. And the other way that people perhaps don't think of as much that makes the Southern Ocean very strongly connected to the wider global ocean is that a large number of the animals that live in the Southern Ocean for part of the year actually migrate in and out on a seasonal basis. And therefore, changes happening to them in the Southern Ocean have consequences at the much larger scale. And by the same token, changes happening elsewhere in the oceans also impact on Southern Ocean ecosystems. And a good example of this is the humpback whale, but many other whale species as well, and flying seabirds, which can travel tens of thousands of miles every single year, transporting the impacts of Southern Ocean change throughout the global ocean system. So I've touched on some of the benefits to global human society of the Southern Ocean, but this slide aims to bring them all together. So there are four main reasons that the Southern Ocean is important for the global human population. As I said, the Southern Ocean takes up a large amount of carbon and therefore plays an important role in regulating our climate. It hosts magnificent biodiversity, which is important for its own intrinsic value, but also has significant cultural value for human beings. The Southern Ocean supports ocean health and productivity throughout the global oceans. And it also provides fisheries and therefore food security for millions of people. And that's fisheries both within the Southern Ocean itself and in regions of the ocean that are fueled by nutrients from the Southern Ocean. So there are a number of climate change impacts on the Southern Ocean, which are summarized here, but I particularly want to draw your attention to those related to ice on the left-hand side of this image. So we've got the retreat of ice that is situated on land. This adds fresh water to the ocean system and therefore changes the nature of these polar ecosystems. And we're also seeing significant changes to the annual sea ice cycle, as Steffi will go on to say in the next talk. And then the temperature indicators in both the deep and shallow ocean indicate that ocean warming is having a strong impact on Southern Ocean ecosystems over a range of scales in time and space. And then our final speaker, Elizabeth, who's joining us from Hobart, is going to talk about number 4 in this image, which is ocean acidification, driven by the fact that the oceans are taking up some of the carbon dioxide that we are emitting into the atmosphere. So I'm going to stop there and hand over to Dr. Stephanie Arndt from the Alfred Wegener Institute, who's going to tell us about the recent changes in Antarctic sea ice. So, Amy.
All right, so can I start, I guess? Yeah, okay, cool. So yeah, welcome also from my side. My name is Stephanie Arndt. I'm a sea ice physicist at the Alfred Wegener Institute for Polar and Marine Research in Bremerhaven. And what you can see here already now on my first slide is the seasonal evolution of the Antarctic sea ice pack. And what you can see and what was mentioned already before by Sean is that we have a really strong seasonal cycle where we have a really large part of the Southern Ocean covered by sea ice in winter time, which is mainly driven by the winds coming down from the continent, the so-called katabatic winds, which push the sea ice always like from the coast off to the north. And then in summertime, it's mainly the sea ice left in the Weddell Sea, which is like east of the Antarctic Peninsula, and then just at the other side of the Antarctic continent, also in the Ross Sea. And this shows already like how virtual kind of the whole Southern Ocean is. And when we look then, in addition to this seasonal cycle and the temporal evolution of the Antarctic sea ice cover, we also see that it's quite varying. What you can see here now is the Antarctic sea ice extent for the month of February, because this is the month of in most cases, of the Antarctic sea ice minimum. And what you can see also here, that it's really, really variable over the past decades. However, this variability was then kind of broken in 2016, where we experienced a really strong negative sea ice development, meaning that we had a really strong retreat of the Antarctic sea ice pack in summertime. And this is also now again shown on the right-hand side in the plot. You can see the sea ice concentration anomaly, meaning the deviation from the mean status over a longer time period. And there also what really changed when we look into the Southern Ocean drastically now, especially in the year 2023, is that we have a sea ice extent retreat that is really shown all around Antarctica in a really circumpolar view. So this is also something that really changed compared to previous years, where we had more like on a regional basis, as what we also know from the Antarctic sea ice land, from the Antarctic land cap. However, this is what puzzled us already in last year's summer. However, when we now look into the winter sea ice extent, we had until last year, basically, we had always also here like quite a variability. However, we always talked about a positive trend. However, now talking about 2023, we had a really drastic change in the Antarctic sea ice cap, which really puzzled us a lot from the perspective of the Southern Ocean researchers, and alarmed us, because what you can see is that this drop in the sea ice extent is not within the standard deviation, like within the kind of normal variation but it's really far below that one. And again, you can see that there are, of course, areas which are more affected also here, but also here in generally speaking, this is again a more or less circumpolar issue that we need to understand. So summing this up, what you can see here now is the sea ice extent anomaly, like again this deviation from the mean state of the Antarctic sea ice pack. And also here again, you can see the sudden loss of Antarctic sea ice starting in 2016. However, what you can see also is that already from 2006 roundabout onwards, we have an increase in the variability also here in the sea ice extent anomalies, meaning that also here the whole sea ice extent seems to get more and more extreme, also just connected to what we observe in general on our Earth. However, of course, for us again here, the big question is, so what is actually the reason for this general sudden loss of sea ice in 2015-16? What is the reason for the strong loss now in 2023? And of course, also, I mean, we do observe this atmospheric warming not only since 2015-16, but of course already much longer. So why was the sea ice in the Southern Ocean not affected so far by that, as we have seen it, or as we see it still for the Arctic Ocean, as we have there already over a much longer time period, this strong decrease in the Arctic sea ice extent. And this, of course, then also connects largely to the question, how is this going to continue? And in order to answer this question, I want to point out that we have already really big issues to just describe the current status of the Antarctic sea ice. What you can see here is a satellite image of the Antarctic sea ice thickness derived from CryoSat-2 from satellite remote sensing for March 2021. You can see the actual derived sea ice thickness on the left and the sea ice thickness uncertainty on the right. And just be careful, so it's different color bars in general. However, what you can see is that the uncertainty of the Antarctic sea ice thickness is around about 50% when putting it on average for the whole Antarctic sea ice cap. And this again shows okay, how should we think about what is coming next if we are not even able to describe what is the current state of the Southern Ocean. And one of the big reasons for this uncertainty when speaking about Antarctic sea ice thickness, which is a really important component, given that we in the end want to think about sea ice volume, is that we have no clue about the snow cover on top of the Antarctic sea ice cover. Because especially for the Southern Ocean, given that we have a year-round snow cover on top of the ice, the snow is a really important component for the whole Antarctic sea ice system in terms, on the one hand, in terms of sea ice growth processes, but on the other hand, of course, also for the whole energy budget. And therefore, the interconnection within the interdisciplinary system between the atmosphere, sea ice, ocean, and of course the ecosystem. And even though the snow has such a huge importance for all these different properties and processes, also here, to be honest, even though I'm studying this now for quite a while, I can tell you we have not a single clue about snow and what is happening there, and what is especially here again happening in terms of processes between the different components, but also on a seasonal basis. However, what we do propose is that the snow is kind of an early warning system for the Antarctic sea ice cover beneath. So we identify the snow as kind of an sensitive indicator for changing atmosphere sea ice interaction process chain. Because what we of course also observed, and this is what you can see on the right panel here, is that also the air is warming above Antarctica and of course also above the Antarctic sea ice cover. However, when we look into our field data for the Weddell Sea, where we study from the Alfred Wegener Institute since many decades, and when we look into the sea ice properties and in the snow properties in terms of internal structure, but also snow thickness, we have not seen any change so far, which gave us always kind of confidence that we are still in kind of a lucky position when talking about the Antarctic sea ice cover. However, we have just seen that the Antarctic sea ice cover did really change. And therefore, it's of course not only enough to look into the snow and the atmospheric component. However, we do also need to consider the Antarctic, the Southern Ocean component. And what you can see here is an image showing the Antarctic in the central, and then the temperature anomalies, again, for the Southern Ocean, but then also how they spread into the different world oceans. And also here you can see that we basically see a general warming of the whole Southern Ocean in all depths. And this then, of course, raises the question, so what is then of this warming of the whole Southern Ocean? What is the consequence for the ocean stratification, for example? So what does that mean for different layers within the ocean in terms of different salinities and temperature profiles? What is here then also the impact on the redistribution of heat in general in the whole system, not only in the Southern Ocean, but the Southern Ocean is the main source of our world's ocean deep water, bottom water masses. And also here, so if we have here then this drastic changes also in the Southern Ocean, this might in the end affect our whole world. And last but not least, these warming waters do, of course, also affect the ice sheets. On the one hand, they do melt them. On the other hand, the melting ice sheets do then also contribute again to a change in the stratification in the ocean, because we have, or we get like more warmer, more fresh waters into the whole ocean column. So this then again just shows there's many different components which are in the end affecting the Antarctic sea ice cover, but also the retreat of the Antarctic sea ice cover does have, of course, also an effect on these properties, given that less sea ice mean in the end more energy that can be transported to the upper ocean and can contribute even more to this warming of the upper ocean layer. So again, when now raising the questions of what is about the future of the Antarctic sea ice cover, unfortunately, I need to say again, we have no clue at all. Because what you can see here now are projections also from the latest IPCC report on the evolution of the Antarctic sea ice extent. And the gray and blue areas, shaded areas, to basically show the uncertainty. And what you can see with that is that the uncertainty is really high, which means yes, we kind of still are in this uncertainty range, but as the uncertainty range is that big, this has, of course, no real implications for the development of the whole system, which just underlines again that there's still a lot of research needs to be done. So to sum that up, I think what I could hopefully show, and what will be also then taken up by the upcoming talks, is that the Antarctic sea ice cover has really drastically changed, and that's pretty sudden, especially when talking about the year 2023. And given that we had now this drastic change, and given that we have no clue why, it's really like when talking about the future of the Antarctic sea ice, it's really uncertain in general. And this really raises the need that we aim for more data, that we aim for more collaborative sense of getting data. And this is why we have now, or we are happy to announce that we got the so-called Antarctica and Zinc project endorsed by the UNESCO as part of the UN Ocean Decade, where we really want to study the Southern Ocean in a really matter of a complex and interdisciplinary system, combined to learn more about the atmosphere, ocean atmosphere, and ice sheet interactions in a really synchronous manner, talking about the whole system around the whole Antarctic continent, and which is really endorsed and also pretty much supported by the Ocean Decade, as I said, by SCA and also by SOOS. So therefore, we're really glad to continue that. And we will start here with a preparatory phase next year, and then hopefully go into the field in 2028, 2029. So to summarizing this all together is, even though we have currently no clue what is the reason or what are the underlying reasons for the change that we observe, we need to understand that whatever is going to happen, it will all just worsen the whole situation. So therefore, if we continue the warming as it is, it will definitely have a huge impact on the Antarctic sea ice on the one hand, but with that, of course, also a huge impact on the Antarctic ecosystem as it was already mentioned by Sean, and with what I now hand over to Letizia. Thank you.
Thank you very much, Steffi, Dr. Steffi Arndt from the Alfred Wegener Institute. And whilst our slides are changed over by the fabulous tech team at the back, it's my pleasure to introduce Dr. Letizia Tedesco from the Finnish Environment Institute, who will talk about the importance of the sea ice ecosystem.
Thank you, Sean. Good morning to all of you in the room, and good morning to our online audience, also from my side. I'm Letizia Tedesco. I'm an ecosystem modeler and based at the Finnish Environment Institute. And I'm also a co-chair of the BEPSII working group. The BEPSII stands for Biogeochemical Exchange Processes as CIs interfaces. And I would like to thank Sean for the invitation to us to contribute to this session. So today I will talk a bit about how CI supports the productivity and the functioning of the Southern Ocean. And let me first tell you a little bit why sea ice is a key habitat for the Southern Ocean. So sea ice is chemically and biologically a very dynamic and a very active environment. There is a variety of biochemical processes that happen within sea ice at the interface with the ocean and with the atmosphere, but also in the atmosphere and in the ocean, which are mediated by sea ice. Is it also a very productive environment? In fact, land-fast sea ice in the Southern Ocean is one of the most productive aquatic environments in our planet. It provides a critical food source. So during winter time, where the food is scarce in the water column, actually sea ice is very critical for the overwintering of several organisms. And it supports key foraging species, especially the Antarctic krill, and I will go back to the Antarctic krill in a few minutes. And finally, and I would like to spend a few words about this, it also provides important ecosystem services. So what are ecosystem services? So ecosystem services are the services that an ecosystem provides to us. So something that we all benefit from them. And in a recent BEPSII paper that was led by Nadia Sterner, which is a former BEPSII chair, we have reviewed the services that CIs, the ecosystem services that CIs provide. And we have found that actually CIs provide all of the 4 categories of the ecosystem services. So habitat supporting services, provisioning services, regulating services, and cultural services. And we not only found this, but we also found that some of these services are directly linked to some constituents of our well-being. And in particular, security, basic material for good life, health, and good social relations. And this is extremely important because for the majority of us, sea ice is something that we see at very far away from us, but it actually has implication and we benefit from it even though we are so far away of it. Maybe not for me that I live in Finland, so I have my bay already frozen, but maybe for the majority of you, you see especially Antarctic sea ice as something very far away from you, but it's actually not, and you actually benefit from it. So going back to our food web, so our sea ice change and impact the height associated food web. So a major driver of change is certainly ocean warming, which literally melt away the sea ice. And this obviously has direct impact on the ice biota. So within sea ice, in the liquid part of sea ice, which is called brines, there is a variety of organisms. You have an example on the right. And the environment is so heterogeneous that actually you have even a zonation with the sea ice. So we have different organisms. There are tiny organisms. So we found bacteria, viruses, we found algae and small grazers and so on. And the majority of the biomass that usually we find in sea ice is actually ice algae. And ice algae is a critical food source for Antarctic krill. And Antarctic krill use sea ice especially for feeding, but also for refuge. And I will go back again to that in a second. And another important example of a direct impact of sea ice on the hydro-associated ecosystem is, for example, the case of Antarctic silverfish. Antarctic silverfish lives underneath platelet ice, which is a special kind of ice which is found under land past sea ice. And use this kind of ice both for hatching and for nursery, and without it, it cannot survive. So what is important to consider is that any change at any level in the food web has an implication, has a cascading effect on the rest of the food web. And any change at a certain level will cause changes in the distribution, in the abundance, in the composition, and in the seasonality of the biological community. And of course, the decrease in sea ice, the disappearance of sea ice, eventually will cause the demise of certain species which are dependent from sea ice for their existence. So I would like to bring your attention to important example how sea ice changes have already impacted the Southern Ocean ecosystem. So the first example is the one of Antarctic krill. So Antarctic krill is one of the most abundant and successful animal on our planet. It's a keystone species in the Southern Ocean because it links the lower trophic level, so ice algae have the food web to the top part of the food web to the top predators. So it transfers carbon along the system. It relies on sea ice, as I said to you already, for food and for refuge. And because it's such an important species, it's also probably the one that has been most studied in the Southern Ocean. So we have records of sampling for more than 90 years. And its distribution is actually circum-Antarctic, but the majority of the population, more than 50% of the population, is actually located in the Southwest Atlantic sector, which is one of the sectors of the Southern Ocean that has been most impacted by climate change and by sea ice decline. So we are really observing changes, and this is shown in these figures on the left side. This is a study that compared 3 different time periods from the early 1920s to the recent days. And it's showing you in red the distribution of Antarctic krill, the density of Antarctic krill. And the more you see red, the more you see Antarctic krill. And as you can see, there's been a contraction southward in time of Antarctic krill. This maybe become even more clear if you look at the histograms, where the bars are the normalized mean of density of krill along 2.5 latitudinal gradients. So you see that in the time from the 1920s toward the 70s, 80s, and now the last few decades, there's been a shift southwards of the population. And there hasn't been only a shift southwards, a contraction, but also a very strong decline in this of the population. So if you look on the right-hand side of these figures, you see that you see the annual mean in density krill above 60 north and below 60 north, and the linear trend. So you see that in both panels, the trend is negative, indicating a decrease, and is especially negative above 60 north. So as I mentioned to you, a change in the population of Antarctic krill, which is so important for the Southern Ocean ecosystem, has direct consequences for the rest of the food web. And the other example that I wanted to show to you is the case of the emperor penguin, which is the iconic species in the Southern Ocean. So the emperor penguin is the largest living penguin, is about 1 meter high, up to 40, 50 kilos. Is endemic to Antarctica, which means that it's not only native to Antarctica, but is the only place that it lives. And it relies on sea ice for its entire life cycle. So it has the peculiarity to do winter breeding. So the colonies arrive on sea ice around March and April, and they depart from sea ice only the next December and January. So they spend on sea ice the majority of its life. And especially the last part of this life cycle, so towards October, November, December, those are really critical times because the chicks are left alone from their parents. So at the beginning, they don't have the right plumage, so they need to stick around all close each other to keep warm. But then the most important period is the fledging, where they acquire this plumage. So they then become able to survive to the Southern Ocean climate. So there's been a recent study who has been analyzing the impact of the last year record low minimum Antarctic sea ice on the population of emperor penguin. in a special area, which is the Bellinghausen Sea, the central eastern part of this area. And what you can see in the upper plot on the left is the sea ice anomaly in 2022 in comparison to the 1991-2020. And the red color indicates a negative anomaly, which means that hasn't been sea ice in comparison to before. And especially the intensity you can see is almost 100%, which means that this was a region where sea ice used to be regularly present, but hasn't been there anymore. And they have studied, so in this area, there are 5 colonies of penguins. So we are aware about, I think, 60 colonies existing around Antarctica. So there are 5 different colonies of penguins and how they have been identified. So for more than a decade, thanks to our satellite images, we have been able to find brown staining of penguin guanos on sea ice. And that's an indication of the presence of the colony. So you see on the right-hand side, those yellow circles indicate where the guano has been found. And as I mentioned before, remember, sea ice needs to be there and the colony needs to have sea ice until at least December in order to survive. But as you can see, in one of these colonies, the Verde Inlet, already at the end of October, sea ice start to break up and there has been no observation of penguin colonies anymore. So in the lowest plot, you see all the 5 different colonies that were studied on the y-axis, on the x-axis, the time period. The dark blue circle indicate an observation of the presence of sea ice and the presence of the colony. The light blue is the presence of sea ice, but already the absence of the colony. And finally, the square orange color indicate the absence of sea ice and the absence of colony. So for 4 out of 5 colonies, already in October, there was no sign of these colonies to be present, which means that all of these chicks have probably died. So this has been a very catastrophic event as a consequence of this such very low sea ice year that we had. So I would like to conclude with just some food for thoughts. Already in 2018, there's been a call for an ecological crisis in the Arctic Ocean after so many years of dramatic Arctic sea ice changes and the fact that I'm a modeler, so we have very little predictability for the future when we are not even able to understand what is happening at the moment. An important action was taken at the end of the SOOS conference last August. SOOS is the Southern Ocean Observatory System. There was a joint call for urgent action for a sustained and coordinated Southern Ocean Observatory System. So the risk that we have at the moment, because the changes in the polar regions are so fast, is that we are not able to catch up with the changes. We are losing predictability. So maybe, and I leave this to you, maybe this is time to call for an ecological crisis also in the Southern Ocean. And thank you all for listening. And I also leave you with this screenshot of it. There is a BEPSII poster in the exhibit area of the Cryosphere Pavilion. If you want to know more about what we are doing, you're welcome to visit. Thank you.
Okay, thank you, Letizia, for that talk. So you've heard so far about the changes in Antarctic sea ice and what they're doing to the ecosystem. We're now going to focus on one of the other main stressors of Southern Ocean ecosystems, which is ocean acidification. And I'm delighted that we're joined today by Dr. Elizabeth Shadwick from CSIRO, the Commonwealth Scientific and Industrial Research Organisation of Australia. So she is coming all the way from Tasmania, joining us on her Friday evening. So thank you very much, Elizabeth. You are center stage and the floor is yours. Over to you.
Thanks very much, Sean. Can you hear me okay?
Is that
Yes.
good for Sam? Try again.
Can you hear me all right?
Yes, that is loud and clear. So over to you.
Thank you very much, Sean. And thank you very much to the organizers. I really appreciate the opportunity to join you today. So as we've heard, the Southern Ocean plays an important role in regulating the global climate. There are 2 services in particular that I want to highlight. We've heard a little bit already about how it dominates the uptake of anthropogenic heat, and it also takes up and stores a significant proportion of anthropogenic carbon dioxide. This service that it provides, of course, comes at a cost, and the cost that I'd like to talk to you about today is ocean acidification. So starting with the problem, which will be no surprise to anyone in the room, we have increasing emissions of greenhouse gases from human sources going into the atmosphere. The figure on the left-hand side shows in red the concentration of atmospheric carbon dioxide between 1958 and present day from observations at the Mauna Loa Observatory in Hawaii. The panel on the right-hand side of the screen puts into context how unprecedented this rate of change is in the recent geological history. So we see from on the right-hand side, present day, and going backwards in time, 800,000 years, pretty regular oscillations of atmospheric carbon dioxide from ice core records from between about 200 and 300 parts per million. This is really at odds with the modern data where we have increased the concentrations to well over 415 parts per million in just 2 centuries. So if you look now back at the panel on the left-hand side, you'll see in green the ocean partial pressure. You can think of that as concentration of CO2. So while the seasonal variability is larger, the ocean is tracking the increase in the atmosphere. And the blue line shows the decrease in pH that goes along with that uptake of anthropogenic CO2. This is the process of ocean acidification. It's a shift in the seawater chemistry that causes a decline in pH as a direct result of the uptake of anthropogenic CO2. Ocean acidification is sometimes also referred to as the other CO2 problem. I have to be honest that I dislike that term because, of course, it's the same problem. Here, I've plotted time series observations from around the world, and they show a clear and consistent picture. There's a decline in pH at the surface of the ocean, which is directly linked to the uptake of anthropogenic carbon dioxide. Very much like the figure that Steffi showed with the penetration into the ocean interior of anthropogenic heat, we see that this signal, while it comes in at the surface of the ocean, is present at depth in all our ocean basins. So the Antarctic is in the middle of that plot. It's a little bit of a tricky one. And you see coming off of it as sort of flags, the Pacific, Atlantic, and Indian Ocean basins. And the red colors are the accumulation of anthropogenic carbon based on observations collected between 1994 and 2007 that show that we observe this signal at depth in all ocean basins. Just a reminder that the Southern Ocean is responsible for about 40% of the uptake and storage of the anthropogenic CO2. Of course, this goes beyond impacts on ocean chemistry and impacts marine organisms and food webs. And I found this paper, which was published in 1973, quite fascinatingly now. It claims that quantitative predictions of accumulation of fossil fuel CO2 have important implications for marine life. And this was a very contentious statement to be making at that time. Of course, we now understand largely via the response of marine calcifiers, or organisms that build skeletons and shells out of calcium carbonate, that indeed decreases in pH have significant consequences. So just briefly, a lot of these impacts are measured via the saturation state. That's a chemical threshold that's given the signal, the symbol omega. If you have values of omega above 1, the waters are considered supersaturated, and the precipitation or the formation of those minerals is favored. When you get omega below 1, you get the chemical favoring is to dissolution. So what's important for organisms is that at increased CO2, which leads to decreased pH and decreased saturation state, they may still be able to form calcium carbonate, but it comes at a much higher energetic cost to them. This impacts a range of organisms, from shallow water coral reefs, who actually need saturation states on the order of 3 or 4, to a variety of mollusks, oysters, crabs, and possibly also things like Antarctic krill, which have been shown to be sensitive to increased CO2. So you've seen more sophisticated versions of this figure already in the session, but this is a simplified Southern Ocean food web. And the photographs on the bottom of the screen are, starting on the left-hand side, a coccolithophore, which is a calcifying phytoplankton, a pteropod, which is, or otherwise called a sea butterfly, which makes a beautiful shell out of an even more soluble form of calcium carbonate called aragonite. And then, of course, the Antarctic krill, the iconic species that we know to be a critical species for providing food to upper trophic levels. So changing the ocean chemistry can have real consequences for organisms that are at the base of food webs, and that has flow-on effects to higher trophic levels and even food security. What do we know about the future? Well, these two plots of the globe show on the left, or with the blue, low emission scenario, and on the right-hand side, a high emission scenario. And the red areas that are plotted in the Arctic and standing out in the Arctic and the Southern Ocean in particular are conditions which are not suitable for marine calcifiers or energetically too costly for them to be able to grow the way that they need to. This schematic comes from the IPCC special report on oceans and cryosphere. And it indicates, if you just focus on the list that is below the acidification with the asterisk next to it, that we know to expect adverse implications of changing pH on organisms, which are very important for the base of the Antarctic food web. We also are expecting an ever increase in global mean sea surface temperature. So again, in red, these are the projections under a high emission scenario, and the blue lines are projections under a low emission scenario. The top panel shows you global mean sea surface temperature, and the bottom panel surface ocean pH. Under the high emission scenario, the red line, we're getting pHs that could well decrease below 7.9, 7.8. That would be devastating for many ocean food webs, and particularly the Southern Ocean, which is extra susceptible to these changes in pH. In terms of the pathways forward, I like this figure. This is from another special report on limiting warming to 1.5 degrees C, something that you're all there to talk about. You see gigatons of CO2 emissions on the x-axis of the plot there against time. And the red line is the trajectory that we're on. The red line is where we're going if we continue with the policies that are currently implemented by our governments. The green line shows the trajectory that we need to be on to limit warming to 2 degrees, and the blue to limit warming to 1.5 with limited or no overshoot. So I think what is very clear is that we need significant and immediate decarbonization if we are going to limit warming to 1.5 degrees. Many of the Southern Ocean ecosystems are depending on us making the right choice here, from things that live at the bottom of the sea, like these beautiful corals, to Antarctic krill that provides food for fish and seals and penguins. So I'd just like to close with what I hope is potentially a positive message, a reminder that the Southern Ocean is changing. It has already changed. The acidification that it has already experienced is unlikely to be reversed even by the most ambitious emissions reduction scenario. But we can still avoid the worst impacts of climate change. We can still avoid widespread year-round calcium carbonate undersaturation if we make the right global commitments and take the right global action. If we limit warming to 1.5 degrees C over pre-industrial values, we can do better for these ecosystems than we have been doing so far. Thank you.
Okay, thank you very much, Elizabeth, for a fantastic and really insightful talk. We've got lots of people in the room who were taking photos throughout your slides and scribbling in their notebooks. So really important contribution. Thank you. So I'm going to attempt now to bring all of that together into a synthesis of what is happening to these Southern Ocean ecosystems. So whilst the final slide deck goes up, you've heard about the changes in sea ice and what they're doing to the ecosystem. You've heard about changes. You've heard about changes in terms of ocean acidification and the threats that they are posing to these ecosystems. And all of this is on the backdrop of gradual but pervasive warming of the ocean from top to bottom, which is pushing these organisms into an environment that they are not used to. So we're not just looking at the warming by itself. We're not just looking at the ice loss and the freshening by itself. And we're not just looking at the ocean acidification by itself. But these organisms are suffering because of the combined and cumulative effects of all of these different changes. And this adds up to more physiological and nutritional and environmental stress than the sum of those individual components. So for the next part, I'm going to show some tables like this from the Marine Ecosystem Assessment for the Southern Ocean, which show the effects or the influence of different climate change drivers on different components of the ecosystem. So firstly, we're going to focus on the zooplankton species like the Antarctic krill that many of us mentioned, That's a type of euphausid. So the next column along is other things like krill. And then we've got copepods, tiny grazing organisms in the middle, salps, which are also an important component of the ecosystem, and then the pteropods, or sea butterflies, that Elizabeth spoke about in the last talk. And what we've got here is the a color coding for how great the influence of each of the processes down the left-hand side is. And I particularly want to draw your attention to the large influence, or the high influence, of sea ice on Antarctic krill and other euphausids. Could you just pop next door and ask them to be a bit quieter? Yeah, thank you. So if we look at the effects of Antarctic sea ice change and loss in the last couple of years, we see that those have very strong impact on Antarctic krill, as Letizia explained to us, and this has important implications for fisheries. There's also a medium impact of sea ice changes on the other zooplankton species, the salps and the pteropods. Then if we look at sea surface temperature, we can see that there is a high impact on all of these types of zooplankton of increasing ocean temperatures. And then to focus in on what Elizabeth just spoke to us about, we see ocean acidification towards the bottom, which has a very strong impact on pteropods, as Elizabeth just explained. And then if we look at krill, in this assessment of influence now, it actually comes out as low, but the reason for that is that we don't yet have enough studies that provide enough evidence that by the definitions of this assessment, we can say that there's a high influence. But what we do know about Antarctic krill is that ocean acidification affects their ability to reproduce, because it has a strong effect on the eggs that krill lay that then become krill and complete the reproductive cycle. The physiological stress that Elizabeth talked about is also particularly pronounced for adult female krill, and particularly those that are pregnant. So we can see that whilst it comes out as low influence in this kind of high level assessment, the influence on specific processes are already being felt and will only get worse as ocean acidification proceeds. And then if we move up the food web or the food chains, we're focusing here on the impacts of climate change on marine mammals and birds. So you see the birds are divided up between those that fly and the penguins, and then we've got seals and whales as well. So in the top, we see that there is a strong negative impact of warming ocean temperatures on all of these types of organisms. If we look at the changes and the decreases in sea ice extent, how large it is, and duration, how long it lasts each year, we can see that there's a mixed effect. Now, this is because there are some species in the Southern Ocean that are very strongly reliant on sea ice, like the Weddell seal, for example, which uses the sea ice to haul out, to rest, to have their young and to raise their young, the emperor penguin that Letizia talked to us about. But there are other species of marine mammals, for example, like the killer whale, that actually does better as sea ice retreats. So that's why we've got a mixed effect. And ultimately, it means that we will have winners and losers in a changing Southern Ocean. But this will mean that the ecosystem structure and the way it functions will change fundamentally. So even though it says mixed impact here, we can expect fundamental changes in the way these ecosystems operate and the services that they provide to humanity. And then the final, on a similar note, but more seriously, if we look at the seals and the whales, on balance, they have a negative impact because there's only one species that benefits, whereas all the rest are negatively impacted by these changes. And then if we look at seafloor systems, these spectacular hotbeds of life where we might not expect them, but these seafloor systems are incredibly high productivity and high biodiversity. They also play an important role in capturing carbon and storing it over timescales relevant for climate change. But we can see that there are also strong impacts of climate change from all of the three drivers that we've covered in this session. So ocean temperature, decrease in sea ice, and ocean acidification. And it's important to note that these seafloor systems are also impacted by the increased mobility of icebergs as the sea ice declines. So the sea ice plays a role in holding the icebergs in place and stopping them moving around. But when you remove sea ice from a region, that means the icebergs can move around more, and they scrape along the seabed and destroy everything in their path. So there are these different impacts that are happening in the ecosystem, and it's the cumulative effects of all of them that really put these organisms and the ecosystems that they're part of under intense pressure. And just a reminder of the slide that I showed earlier on the ecosystem services of the Southern Ocean as a primer for the next slide, which shows a risk assessment of climate change impacts on these ecosystem services. So these things that Southern Ocean ecosystems provide directly to humankind, both near and far from Antarctica. And I'll particularly draw your attention to the top section, which is fisheries, in particular the Antarctic krill, where we can see a very high level of risk across ocean temperature, ocean acidification, and overall. And that's because of what Elizabeth explained about the effects of ocean acidification being accelerating and getting much worse over the coming decades. And then for the other fisheries species, there is currently an intermediate risk, but we can expect this to get worse if we do not stick to the 1.5 limit of warming, whereas if we do stick to that limit, then we can see these risks reducing. And if we look at the supporting ecosystem services, these ones at the bottom, we can see that there is an intermediate risk to the role of the Southern Ocean in supporting ocean health regionally and at the global scale. So this is all done based on if we continue on our current trajectory. But the most important point to make is that if we stick to that 1.5 degree warming limit, these risks are reduced substantially, and the impacts of those three complementary drivers on the ecosystem are also reduced substantially. So by way of concluding, and I'd like to do that by showing this piece of artwork. I think as scientists, we are quite good at communicating to audiences that are not scientists, but we are nowhere near as good at communicating as artists. So I think it's really important for the different communities to work together to convey these messages as far as they need to be conveyed. So with huge thanks to Eve Brennan, who is the artist here, and this image clearly shows on the left-hand side that if we limit warming to 1.5 degrees C, the ecosystem remains stable. And not only that, but it can recover from any short-term damage that is done to it because its base level of ocean health is sufficient to allow that recovery. Whereas if we slip into the image on the right, where we have warming above 2 degrees, if we fail to stick to the Paris Agreement, then we see these dramatic changes that we've talked about in this session, and their impacts cascading through the food webs and restructuring and changing the nature of the whole entire ecosystem, as well as the ecosystem services that the Southern Ocean provides to humanity, both near to the Southern Ocean and many thousands of miles away. So I will leave you with this image, which I think captures very nicely the beauty and the magnificence of the Southern Ocean, but also its fragility to the changes that we've discussed in this session of warming, loss of ice, and acidification. And I'll leave you with the message that to avoid severe and irreversible damage to ocean ecosystems and the services that they provide to global human society, we need deep and urgent emission cuts to keep warming within the 1.5 degrees C limit, in line with the Paris Agreement. And as Elizabeth said very nicely, these cuts don't just need to be deep and urgent, but they need to be sustained at all levels of society. And in order to facilitate that, we need to make the decisions that lead to this outcome at this COP28. And I'll leave it there. We'll go into a short panel discussion now. So we invite questions from the room and the online audience. So Elizabeth is going to join us again from Hobart, Australia. And I invite Letizia and Steffi to join me at the front. Okay, so are there any questions?
It's not that we don't have enough stressors on Antarctica, but I wonder if any of you have worked or has any information on the presence of microplastics.
Yeah, who would like to take that? Shall I take that? I'm happy to take that. Yes, so up until about 10 years ago, we thought that there were no plastics in Antarctica, no microplastics at least, but they have now been found in every component of the Antarctic system, from the phytoplankton at the base of the food web, in the small consuming organisms, the zooplankton, all the way up to the large whales and seals and penguins. So they, having thought that Antarctica might still be pristine in that regard, we now know that that is absolutely not the case. There has been some work done on what the sources of those microplastics are, and the majority of them are from many thousands of miles away and are transported there on the ocean currents, but there are actually sources from within Antarctica itself, which tend to be associated with parts of the coastline that are visited by human beings, either by tourists or by scientific research parties and by the ships that traverse the Southern Ocean on a regular basis. So there is now regulation in place as to how to limit this as much as possible, but it is certainly an additional stressor on the system that we can expect to add to the overall stress and ultimately to weaken the resilience of these systems in the face of other changes.
Are you aware of any line of study regarding the impact? I mean, because basically the impact of the microplastic would be.
Yes, so in terms of the larger organisms, there is not much work that's been done yet, but there are hypotheses about modifying physiology and in particular feeding processes. For example, baleen whales that have these large baleen plates that capture the zooplankton. They could easily be collecting microplastics as well. But what has been shown is that in zooplankton communities, the microplastics are of a similar size to phytoplankton, and therefore they can be mistaken by the zooplankton as phytoplankton food. The zooplankton then consume them and they block up their feeding apparatus and can ultimately cause death by starvation because they provide no nutritional benefit and they block up the feeding apparatus. There is a project that is quite young, it's just starting to look at the actual effects on phytoplankton themselves. because phytoplankton sinking is a large source of carbon to the seabed and therefore a mitigator of climate change. But there is a hypothesis that the presence of microplastic within a phytoplankton community could alter the rate at which phytoplankton sink by making them more buoyant, and therefore could interrupt that process, which is very important to us in terms of mitigating climate change, but also in terms of the way that the ecosystem functions.
Thank you very much.
Okay. Any other questions? Has somebody got a question for Elizabeth to thank her for joining us from Hobart on her Friday evening?
I think I do. If it had to do with ocean acidification.
Yeah.
What does it look like when it comes to how does it manifest in animals? Like do shells become thinner or do they malform when they're unable to construct, their basic?
Both things have been observed. So I mentioned it was energetically more costly for an organism to create a shell or a skeleton. It can also be possible for their shells to dissolve. So juvenile organisms are found misshapen. It can disproportionately affect young stages of calcifying organisms. All that, yeah.
And is there a number that you can put on, let's say, about the production of diatoms? How is it more or less? How much less?
So diatoms are not calcifying organisms. Diatoms are silicifying organisms. So they require silica. And so they are not in particular under extra threat from acidification, at least as far as we understand. Coccolithophores, the one that looks like it has kind of armored plates around it, those have been shown to dissolve. There have been studies that compare sediment core records of more modern organisms, so things that would have grown in the ocean over the Anthropocene, over the last 200 years, to organisms that would have grown in waters that did not already contain this anthropogenic CO2 signal, and it has been shown that they are thinner and smaller. So it is measurable. I would hesitate to put a number on it, but it's certainly a measurable effect.
Okay, any other questions from in the room or online?
Number online. The first is, those sea ice typically hold back before movement of western Antarctic glaciers. The stress shows features in the sea ice. Can we monitor the stress within the sea ice? And does this melting of sea ice impact the speed of glaciers? So that's a swing.
Yeah, I think this is like one general answer to that question. So yes, of course, the sea ice has kind of a stabilizing effect on the shelves behind, which means that if now the sea ice is retreating more and more, the fast ice, so ice that is connected to the shelf ice, might then also break up earlier, which has an impact on the one hand on the ecosystem, on the penguins that were mentioned, but on the other hand, it has really huge impact also on the ice shelves behind, because the earlier the ice is breaking up, the more time is also for the ice shelves behind to just like proceed towards the north and also to get unstable. And therefore, yes, there is a direct connection. And this is also now something that we are fearing, that the whole system, the coupled system, ocean, sea ice with the glaciers and the back is getting more unstable in general.
Another virtual one, if you're right now. Do you incorporate vertical rivers like in Greenland, atmospheric rivers, more atmospheric dynamics?
Can you just repeat?
Yeah, do you incorporate atmospheric rivers in your modeling it's the more of atmospheres?
I'm actually not sure. So these are like atmospheric processes, and I'm not sure if this is done for the Southern Ocean. I'm aware of studies in the Arctic Ocean, but I'm not sure.
Me neither, to be honest. So I know that we do observe atmospheric rivers more and more also in the Southern Ocean, and that they do impact a lot the local weather pattern, especially also close to our German overwintering base. But I could not say whether this is already included into climate models or not. Sorry for that.
Okay, I've got any more questions from the room?
Well, you showed a slide with sea ice anomaly, 100% anomaly.
Yeah. Negative anomaly.
How is that possible? So are you saying there was no sea ice?
There was no sea ice at all at the time of the year that it used to be there, at least in comparison with that time period, which was, if I remember right, between 1991 and 2020. So that was a mean. Is that possible? Because obviously sea ice is retreating. So that means that at that time of the year that it used to be sea ice, there was not there anymore. And the penguins are long-lived organisms, so they have sort of capacity to, because they are so long-lived, to sort of resilience. But actually, so 1 to 1 year damage or this large layoff may not impact the entire population. But if this continues to happen, I mean, the longer term is that this frequency will obviously disappear. So they have been observed to move around. So we will see in the next years to come where they will be able to move around and survive. Yes.
You showed an area of the Antarctic Ocean. What size are we talking about?
It's quite a large part. So it's the northern part from the West Antarctic Peninsula. Do we have an idea how big it is? In numbers, not around into millions, but probably less. Square kilometer of that's some part of the Southern Ocean that has been more affected by sea ice for a long time. So we have been seeing this kind of a shift, trend shift around 2016, but this part of the Southern Ocean has been affected by sea ice changing for a long time.
Okay, just to get my bearings, so where is this facing? If we're looking north from that area that you're talking about, what are we looking at? Are we looking at Australia or are we looking at Patagonia?
So we are looking at the Patagonia.
Okay, I think given the time, we've already overrun very slightly, only very slightly. So I'll just have some closing remarks. So hopefully we've managed to convince you over the course of the last hour or so that Southern Ocean ecosystems are under severe threat from climate change because of ocean warming, changes in ice dynamics, particularly sea ice, and ocean acidification. But we're not so worried about these effects individually. It's the combination and the accumulation of these effects that's really putting these ecosystems under pressure. And that's threatening ecosystem services that these ecosystems provide to humanity at the global scale. So I hope we've also managed to convince you that these ecosystems are under much more severe threat if we exceed the warming threshold of 1.5 degrees. And if this happens, then these ecosystems will be at risk of irreversible damage over many thousands of years. Whereas if we keep warming within that upper warming limit of 1.5, these ecosystems will remain intact and they will be able to recover from short-term perturbations. So on behalf of Southern Ocean ecosystems, it's absolutely imperative that we keep warming within that 1.5 degree limit. And the sooner we do that, the better. So we need to make the commitment to do that at the political level at this conference. So if you are negotiators or you have close links to negotiators, please do pass that message on so that we can make the cover decision and the decision from the global stocktake of this conference, or that is being finalized at this conference, as meaningful as possible for the ecosystems, but also the global human population that needs these ecosystems. So I'll leave you with that thought. And I'd like to thank again Dr. Elizabeth Shadwick, who's joined us this evening from Tasmania, Dr. Stephanie Arndt from the Alfred Wegener Institute, Dr. Letizia Tedesco from the Finnish Environment Agency, and the Southern Ocean Observing System for putting on this event. And my final thanks is to the fabulous team at ICCCI, the International Cryosphere Climate Initiative, for running the Cryosphere Pavilion, but also being an amazing voice for the cryosphere within these negotiations and across policy circles. So thank you all for coming, and we'll be hanging around afterwards if you'd like any further discussion. Thank you.
Thank you.